wabarakatuh dan salam sejahtera. Yang berbahagia Tuan Sri Wahid Umar, Pengurusi Lembaga Pengarah UKM dan semua profesor dan rakan-rakan daripada Fakulti Kedokteran dan juga UKM, and also welcome to our guest from the embassy. Pada pagi ini kita memberi penghormatan kepada Profesor Dr. Muhammad Makmun Ibni Rilis daripada Fakulti Kejuruteraan dan Alam Bina yang akan menyampaikan syarahan beliau yang bertajuk Readerless RFID, A Pathway of Compactness and Simplicity. Profesor Dr. Makmun dilahirkan di Patna, Bangladesh pada tahun 1963. Beliau mendapat pendidikan menengah di Sekolah Bahasa Penuh Kolej Kadet Rajahi, iaitu sebuah kolej yang dimiliki oleh tentera Bangladesh. Mungkin kita punya RMC lah, betul kan? Setelah menamatkan persekolahan di peringkat menengah, beliau kemudiannya melanjutkan pengajian di Universiti Rajahi, Bangladesh dan berjaya memperolehi ijazah sarjana muda sains pada tahun 1988 dan ijazah sarjana sains pada tahun 1990 dalam bidang fizik penggunaan dan elektronik. Seterusnya, beliau menyambung pelajaran di peringkat ijazah Dr. Falsafah PhD di dalam bidang sains dan kejuruteraan dari Universiti Ibaraki, Jepun pada tahun 2017. Saya tak ada detail ni, tapi beliau telah berkahwin dengan Nazneen Nahid yang ada di sini dan telah mendapat 2 orang cahaya mata. Kejayaan akademik beliau bermula di Universiti Multimedia pada tahun 2001 sebelum menyertai Universiti Islam Antarabangsa Malaysia pada tahun 2006. Beliau kemudiannya memulakan kejayaan akademiknya bersama UKM pada Disember 2008 dan sekarang merupakan seorang profesor di Pusat Kejuruteraan Elektronik dan Komunikasi Kehadapan atau PKEK di FKAB. Profesor Dr. Makmun adalah seorang penyidik yang berwibawa dan telah memperolehi banyak pengiktirafan di peringkat kebangsaan serta antarabangsa. Fokus kajian beliau adalah dalam bidang reka bentuk litar bersepadu Integrated Circuit IC, penderia bioperubatan dan sistem rumah pintar. Beliau telah menghasilkan lebih 180 artikel jurnal penyidikan, 150 kertas persidangan dan 5 buah buku penyidikan dan beberapa bab dalam buku di dalam pelbagai topik berkaitan dengan reka bentuk litar bersepadu atau IC, penderia bioperubatan dan sistem rumah pintar. Sehingga kini sebanyak 9 paten hasil penelitian beliau telah berjaya dikeluarkan. Hasil penelitian beliau juga telah dipetik sebanyak hampir 3,000 kali dan each index beliau adalah sangat tinggi, iaitu 24 Scopus each index. Dalam bidang penyidikan, Profesor Dr. Makmun telah menerima 56 grant penyidikan bernilai jumlahnya lebih daripada 12 juta dari pelbagai sumber di dalam dan juga di luar negara. Hasil penyidikan yang dijalankan juga telah memenangi beberapa anugerah antarabangsa, antaranya anugerah utama inovasi reka bentuk dan artikulasi antarabangsa di UiTM Perlis, anugerah kedua terbaik di Hari Telekomunikasi Dunia dan Maklumat Masyarakat oleh Kementerian Pos Komunikasi dan Teknologi Maklumat Bangladesh, dan juga merupakan penerima anugerah pengarang terbaik di United Nations Pavilion Expo Shanghai, China pada 2010. Kewibawaan dan ketokohan beliau dalam bidang kepakarannya mendapat iktirafan dari pihak apabila beliau dilantik menganggotai beberapa organisasi, antaranya beliau adalah senior member IEEE, Institute Electronic and Electrical Engineering, Institut Kejuruteraan Elektronik, Maklumat dan Komunikasi, dan ahli bersekutu dan juga sarjana pelawat di Pusat Antarabangsa Abdul Salam bagi teori fizik, iaitu International Center for Theoretical Physics di Itali. Beliau juga pernah menjawab pengarah dan bagi 3 program yang dilaksanakan di Bangladesh, Malaysia dan India yang ditaja oleh Pusat Antarabangsa Abdul Salam bagi teori fizik Itali, masing-masing pada tahun 2008, 2011 dan 2019. Kalau saya masih ingat di fakulti, beliau merupakan orang yang behind untuk fakulti kedokteran dan UKM, jadi kita punya associate partner dengan ICTP yang membolehkan fakulti menghantar beberapa pensyarah yang ditaja oleh ICTP untuk mengikuti kursus-kursus di Itali. Beliau juga pernah menjadi pengarah kumpulan penyelidikan reka bentuk cyber prestasi tinggi di bawah Penyelidikan Malaysia dan Jaringan Penyelidikan MyRAN Malaysia dari tahun 2007 hingga 2010. Profesor Dr. Mamun juga pernah memberi khidmat sebagai lembaga pengarahan bagi Advances in Electrical Engineering Hindawi Publishing Company dan editor 2 buah buku Radio Frequency Identification dan RF System Circuit dan Komponen yang telah diterbitkan oleh Intel Publisher pada tahun 2012 dan 2018. Beliau juga telah dilantik sebagai pengurusi persidangan antarabangsa penjuruteraan elektrik, elektronik dan sistem terhadapan International Conference in Advanced Electrical, Electronic and System Engineering. Sepanjang kejayaan akademiknya, Profesor Dr. Mamun telah menyelia lebih dari 100 orang pelajar siswaza dan pasca siswaza dan 45 daripada mereka telah menamatkan pengajian. Beliau juga telah membangunkan kurikulum bagi program ijazah sarjana muda penjuruteraan elektrik untuk College University Infrastructure Kuala Lumpur (KLUC), dan juga telah mereka bentuk dan membangunkan khusus basic RF bagi skim kemahiran semula siswaza di Design and Development Penang Skill Development Center. Runding akademik bagi ijazah sarjana muda program penjuruteraan di Kolej Antarabangsa KBU, ahli panel penasihat industri dan ahli lembaga pembelajaran di Jabatan Penjuruteraan Elektrik Elektronik Kolej Universiti Infrastruktur Kuala Lumpur. Profesor Mamun juga pernah menjadi profesor pelawat di Sekolah Penjuruteraan Elektrik Elektronik Universiti Chung An di Seoul, Korea, dan Jabatan Penjuruteraan Elektrik dan Komputer University of West Indies di Trinidad dan Tobago pada tahun 2010. Profesor Mamun juga adalah antara penilai semula Geran Pendidikan di Malaysia dan luar negara, antaranya penilai semula Geran Cadangan bagi Organisasi Penyelidikan Saintifik Kementerian Hak Ehwal Ekonomi Belanda, Pusat Sains dan Teknologi Nasional Kazakhstan. Kini projek penyelidikan beliau adalah pendiri bio berkapasitan tanpa sentuh, analisa ramalan bagi sistem rumah pintar, reka bentuk penerima penghantar terima CMOS dan IC RFID. Jadi hadirin dan hadirat yang saya hormati sekalian, saya pasti tajuk RFID ini sangat menarik kerana kita dalam kehidupan kita banyak kita jumpa ni lah aplikasi RFID yang betul rapat dengan kehidupan kita. Jadi saya dengan sukacitanya mempersilakan Profesor Dr. Mamun dari Fakulti Kedokteran dan Alam Bina untuk menyampaikan syarahan beliau yang bertajuk Readerless, RFID, A Pathway of Compactness and Simplicity. Sekian, Assalamualaikum warahmatullahi wabarakatuh.
Future network and services for recognition schemes along with wireless technologies require innovative ideas that should focus on the improvement of the environmental, institutional, industrial, healthcare and transport sectors. At present, wired services manage to supply infrastructure, whereas wireless services create available mobility, miniaturization, and inexpensive electronic devices that will provide access points in any location. Wireless technology and devices are currently essential components of our daily lives. In the near future, wireless network technology will be used to link consumers with businesses that cater to their specific needs. Radio frequency identification is in short, RFID is a generic term used to describe a system that wirelessly transmits the identity of an object or a person using electromagnetic radio waves, which is an alternative to barcode. RFID is an automatic identification system relying on storing and remotely retrieving data using tags or transponders. Among different types of wireless technologies, such as barcodes, sensor networks, and automated highways and factories, RFID is the most popular emerging system. RFID exhibits a promising future in various wireless network sectors, either as a standalone system or as part of a large network infrastructure because of the superiority and efficiency of its technology. Barcode technology does not have all the features of RFID technology because a direct visual connection between the reader and the barcode is required to read information. Moreover, reading fails if dirt or other obstruction exists between the barcode and the reader. An RFID reader does not require any physical or visual contact to read information from the tag. In an RFID system, defined standards, defined distances, and various frequency ranges are required. Germans invented the first passive RFID system during World War II. In 1935, the radar system was invented to detect incoming aircraft. However, this system could not differentiate between friendly and enemy aircraft. The Germans discovered that if pilots rolled their planes as they returned to their base, the change in radio signal would be reflected back. This crude method alerted the radar crew on the ground that the incoming planes belonged to the Germans and were not hostile. This method is acknowledged as the first passive RFID system. The identification friend or foe system, which was invented by the British, is known as the first active RFID system. In this system, a transmitter which received radar signals and broadcast them back was placed in each aircraft. Eventually, this transmitter became known as the tag in current RFID system. In 1973, the first active and passive RFID transponder or tag with a rewritable memory was patented. This tag was used to open doors without a key. The first commercial application of an RFID system was recorded in 1980. In this system, the tag contained information about a product or object that was written and read from an RFID reader. An RFID system has three main components: a transponder, an interrogator or reader, and an application in PC. The two key parts of an RFID system are the transponder and the transceiver. An RFID transponder is an integrated circuit with an antenna that acts as a storage medium. A reader reads tag data using wireless communication. The first 12-bit read-only RFID tag was built using CMOS logic chips and hybrid thick film in approximately in 1976. In this tag, circuitry covers half of the tag area. In 1987, a 128-bit read-only tag was built using a custom CMOS integrated circuit with off-chip components, where circuitry covers a quarter of the tag area. In 1999, a 1024-bit read-write tag was built using a single custom CMOS integrated circuit, where circuitry covers an insignificant portion of the tag area. A data carrying device that is fixed onto the items to be identified in an RFID system is known as a transponder or tag. A transponder is mainly used to carry the ID information of an object. An RFID transponder is composed of an antenna, a radio frequency transceiver section, an analog detection rectification section, which detects and rectifies RF power into an equivalent DC voltage, and lastly, a digital control section that is either a microprocessor or other digital systems. An RFID system can be classified into active, semi-passive, or passive, depending on power sources. An active transponder has its own power source, typically a battery, to run the chip and transmit data to the interrogator. An active tag allows very low-level signals to be received and can still generate a high-level signal to be transmitted back to the interrogator. An active tag remains in sleep mode until it receives a wake-up signals from the reader. The data carrier changes to operating mode as soon as the tag receives the wake-up calls. Then the tag returns to sleep mode after completing data transaction. Data transmission that does not require an integrator is possible because an active tag has an onboard battery. An active transponder has a finite lifetime and longer reading range than other types of transponders. A passive tag is batteryless and uses the energy induced by the electromagnetic wave from the reader in the antenna to power up the chip and transmit data back to the reader. Passive tag reflects energy from the reader or receive and temporarily store energy to generate the response of the tag to the reader. A semi-active or semi-passive transponder, depending on the manufacturer, has an onboard battery too. However, the battery is used only to operate the chip. That is, the tag lies inactive until receiving a signal from the reader. Like an active tag, the energy in the electromagnetic field is used to wake up the chip and transmit data to the reader. Semi-active or semi-passive tags are occasionally called battery-assisted passive tags. RFID is the most popular emerging system and its increasing demand spreading to business, daily life, residence, educational system, etc. RFID has been applied to key cards, travel cards, and long-term animal tracking recording. RFID is becoming increasingly popular in industries for applications in quality control, logistics, and cargo tracking. Many industries and services are interested in RFID systems for product tracking, supply chain and system management, pet tracking, hospital management, and inventory system management. Wireless communication is the fastest growing topic in the communication industry because of its extensive media coverage and positive public image. At present, approximately 3.7 billion people worldwide use wireless technologies, such as cellular phone systems, radio frequency identification, and wireless network. Moreover, most residents of developed countries utilize this technology in their daily lives and businesses, whereas most residents of developing countries are on their way to integrating these technologies into their lifestyle. The wired network is expected to be replaced by wireless network in all residential, business, and education systems. RFID system is used in different applications such as toll plaza payment, supply chain management, reverse logistics, shipment tracking, asset tracking, animal identification, healthcare, apparel luggage, laundry, etc. In all these applications, tags can be attached to almost anything such as pallets or cases of products, vehicles, company assets, or personal items such as apparel, luggage, laundry, people, livestock, or pets. High-value electronics such as computers, TVs, camcorders. In the healthcare sector, the increasing focus on infection control is attracting interest in the use of RFID technology to track and classify medical instruments. The technology exhibits immense potential in improving the efficiency of the supply chain, ensuring the safety of patients, and reducing human errors in healthcare processes. Medication management and the monitoring of critical care equipment represents other interesting application areas. A pharmacist can fill a prescription from a bottle implanted with an RFID chip to confirm the authenticity of its contents. Some organizations use RFID to track mail, manage hazardous materials, collect tolls, and warn people about tsunamis, bird flu, and other natural disasters or events. Malaysia was the pioneer in e-passport application, and now it is being adopted in many countries. RFID, with its numerous potential applications and accompanying technologies, represents more than an incremental step toward the improvement of a large number of companies and businesses. Driven by robust application opportunities in the retail and healthcare sectors, the global market for RFID tags is projected to reach $6.9 billion by 2020. Led by regional government initiatives to promote the adoption of this technology across various application areas such as transportation, national IDs, and electronic identification and authentication, the United States and the Asia Pacific currently hold the largest market, which is estimated to become the highest growing market with a compound annual growth rate of 8.5% during the study period. Under the third industrial master plan of Malaysia, the logistics industry is targeted to grow 8.6% during the planned period, that is between 2006 to 2020, and is projected to contribute 12.1% to the country's gross domestic product by 2020 from the use of RFID technology. In addition, the volume of total cargo handled by ports is expected to increase by more than threefold, from 252.6 million tons in 2005 to 751 million tons in 2020. While the volume of air cargo trade is projected to increase by more than twofold, from 1 million tons in 2005 to 2.4 million tons in 2020. Rail cargo volume, meanwhile, is expected to increase almost fivefold, from 4 million tons in 2005 to 18.6 million tons in 2020. RFID exhibits a promising future in various wireless network sectors, either as a standalone system or as part of a large network infrastructure because of the superiority and efficiency of its technology. An RFID tag is represented by an electronic product code in a short EPC, which is a UHF band standard defined by ISO 18006C, also known as Gen 2, and managed by EPC Global. Moreover, this standard aims to improve identification and operation security in a multi-reader environment for the UHF band. An EPC is either a 64-bit or 96-bit identifier in which namespace is segmented into 4 hierarchically encapsulated partitions. The 2 bits header identifies the EPC version number and allows different length or types of EPC, such as type 1, 2, 3, and 4. The 21 bits EPC manager identifies the manufacturer of the product to which the EPC is attached. The 17-bit object class identifies the exact type of product, which is generally the stock keeping unit. The 24-bit serial number identifies the unique ID of an item. RFID readers communicate with tags through an RF channel to obtain identification information. This communication may be a simple ping or a complex multi-round protocol, depending on the type of tag. In an environment with numerous tags, a reader may have to perform an anti-collision protocol to ensure that communication conflicts do not occur. Readers have many forms, operate under different frequencies, ranging from 30 kHz to 300 kHz, referred to as low frequency, and 3 MHz to 30 MHz, referred to as high frequency. High-frequency band RFID operates at 13.5 MHz, which is widely used in industrial application. Ultra-high frequency, that is 300 MHz to 3 GHz band RFID operates at 9 MHz and provides higher data rate and has a smaller antenna than HF. Other frequencies, such as 2.45 GHz and 5.8 GHz, which have smaller antenna and are suitable for less populated frequency ranges, are also suggested for RFID operation. The use of RFID remains limited because of the few issues, namely standardization concern, easy to jam, which is disastrous in case of hospitals and military, reader collision, that is one tag many readers, high implementation cost of the vendor-specific reader, limited address space of the transponder, and restricted local mobility. With nearly all data security algorithms, with the exception of the strongest being subjected to successful brute force cracking using portable or network computing resources, the cryptographic capabilities of tags have become an important consideration in their selection. The information inside RFID tags is vulnerable to alteration, corruption, and deletion. A research survey conducted by NECTAG found that delay in RFID deployment occurred due to 4 factors: RFID cost, standard, technology suitability, and lack of knowledge. In any RFID application, the reader is the most expensive part of an RFID system. Nevertheless, the design of an RFID transponder without a vendor-specific reader is a challenging task. Moreover, the process faces several difficulties, such as designing a high-performance transponder, reducing power dissipation, and fabricating a transponder chip that integrates all the significant modules. In addition, several major components of an RFID transponder, such as voltage control oscillators, frequency dividers, transmit-receive switches, baseband processors, memory read-write circuit sense amplifier, and charge pumps should be redesigned, characterized, and optimized in terms of cost, security, mobility, and scalability. To address these issues, a robust wireless network interface card, in short WNIC, can be used to communicate with the transponder instead of a costly reader. With the capability to enable low cost, dissipate low power, ensure compactness, and produce less heat waste from the perspective of a fabrication process that is compatible with existing processes, a readerless RFID transponder is widely believed to be the technology that will be developed in the CMOS process. The need for a low-cost and low-power system is growing because of the increasing demand for durable, mobile, and efficient identification systems. Moreover, contemporary RFID systems have to be redesigned to eliminate the need for highly expensive readers. The possibility of achieving significant performance improvements in the CMOS process is more important than that in other processes available in the research area. Thus, a readerless RFID transponder has important implications in system design for successful operations. The implementation of a readerless RFID system should ensure several factors such as privacy, standards, data management, mobility, and scalability. The use of Wi-Fi networks and an Internet Protocol version 6, in short IPv6 address as tag IDs can overcome the aforementioned drawbacks of an RFID reader. In such system, an innovative RFID tagging system is introduced using a Wi-Fi network. There are 4 phases in designing readerless RFID, namely mapping EPC 64-bit with IPv6 address, EPC IPv6 tag communication with WNIC, EPC receiving technique, and EPC IPv6 tag circuit design. IPv6 succeeds IPv4 and provides end-to-end connection with 128-bit address space. A 128 bits IPv6 address is becoming an essential future network infrastructure because of its large address space. IPv6 uses a unique local address with an anycast communication scheme, which exhibits self-organization and service discovery via auto-configuration. In addition, enhanced service capabilities using IPv6 header information are provided. Moreover, IPv6 addressing facilitates multi-homing. IPv6 exhibits scalability, mobility, security, and multicast anycast features, thereby making it an in-demand addressing scheme at present. IPv6 helps IP network devices to communicate by providing secure and specific addresses to each device. IPv6 eliminates the address depletion problem as well. Electronic product code, extended unique identifier, and medium access control addresses are examples of identification codes. Moreover, most identification codes utilize a large number and thus require a huge address, and a 128 bits IPv6 will be the right choice. A combination of IPv6 and wireless systems such as IEEE 802.11 protocol will reduce the current problems of dual scarcity in an IP address, quality of service and security from the IP side, and lack of spectrum and bandwidth from the wireless side. Instead of using an RFID reader, the system can simply use WNIC to receive information from the mapped EPC IPv6 transponder. The proposed system eliminates the need for an expensive vendor-specific RFID reader and provides a global ID number to every object. An IPv6 address format is subdivided into 2 portions. The first 64 bits are defined as the subnet, whereas the last 64 bits are defined as the interface ID. The subnet or network prefix is used to define the physical location that is predefined by the router. An interface ID is required for unique identification or tracking. A simple algorithm is used to convert a MAC address into a modified UI64. In this algorithm, the 7th bit of MAC, which is also known as the global flag, is reversed. Then extra bits are placed in between the 3rd and 4th bytes of that address. This UI64 is used as the interface ID of an IPv6 address. Similarly, EPC 64 bits can be inserted into the IPv6 address structure to be used as an interface ID in a readerless RFID system. Thus, product information inside EPC 64 bits will be held by the IPv6 address structure to track any product destination information. In this manner, all product information previously held by the IPC will be mapped directly onto the interface ID portion of the IPv6 address. Thereafter, this mapped address should be stored in RFID transponder memory, which can be a non-volatile memory such as EEPROM structure. Thus, each RFID tag becomes addressable in the IPv6 network and physical location identification become possible. The RFID tag will store the entire EPC IPv6 address by using the mapping mechanism of this address. The RFID tag can be consigned to a range of 3 to 300 feet at 2.4 gigahertz in the industrial, scientific, and medical frequency band. When an IPv6 RFID tag enters a Wi-Fi network, the system that contains WNIC will recognize it first. WNIC will broadcast a message, and all RFID tags in the Wi-Fi network will receive this message. After receiving the message, the RFID transponder will send the acknowledgement packet. WNIC will then obtain the RFID transponder IP addresses from the acknowledgement packet. In a readerless RFID transponder system, the IP address can be produced through the IP address generation process. The generated IP address will be mapped with the RFID PC and stored in the RFID tag or transponder. The RFID tag data received by WNIC will be processed using an application to decrypt the EPC ID from the IPv6 frame. However, EPC and IPv6 are interpreted differently with varying job scopes in various applications, that is, the partition identifiers in the two identification schemes have different interpretations. The EPC and IPv6 namespaces are effectively managed by product manufacturers and network administrators because of their interpretations. In the proposed system, a readerless RFID tag includes several ICs that are subdivided into four main modules, namely the RF front-end, baseband processors, MAC processors, and memory block. In this proposed transponder, the tag IC front-end, baseband processor, MAC, and memory block are required to build a complete readerless RFID. In an RFID system, an antenna is connected to the RFID transponder to transmit or receive signals for data collection and communication. This work aims to produce a low-power fabricated IC for the proposed system. Non-volatile memories such as EEPROM, SRAM, and FRAM are required to store the data buffer of the EPC mapped IPv6 address in a readerless RFID transponder. The transmitter and the receiver are the most significant modules in the RF front-end. The performances of these two modules depend on voltage control oscillator, transmit receive switch, and frequency divider circuits. The baseband processor consists of three main circuitries: a decoder, an encoder, and a processing unit. A MAC unit includes four major blocks: phase control logic, state control unit, contention number generator, and handshaking message generator. The performance of the memory block mainly depends on the sense amplifier for the read operation and the charge pump circuit for the write erase operation. The front end consists of a receiver and a transmitter. The receiver is modified by adding Wi-Fi features such as frequency and tuning range to comply with WNIC features. A fully integrated CMOS transceiver is an essential component in every wireless communication system to ensure highly efficient signal receiving and data transmission. Certain key parameters such as power dissipation, frequency, tuning range, phase noise, linearity, and insertion loss have significant effects on the design of a transceiver because these parameters determine whether a design transceiver will comply with the desired standards. Moreover, high-performance VCOs, ring oscillator type ILFDs, and tier switches are essential elements in the front end, which generally connects the receiver or transmitter through a common antenna that relies on a control signal. In transmission mode, the antenna and the transmitter are connected through a control signal while the receiver is protected from any harm by using a powerful signal. A similar scenario is observed during the reception mode, and thus the transmitter is kept separated to prevent the loss of low signals. In this design, a simple binary phase shift key transmitter and receiver based on the direct conversion approach has been considered. One of the essential blocks in an RF transceiver is the frequency synthesizer or local oscillator, which is used for carrier generation and system clocking. The popular local oscillator for wireless communication is the phase locked loop based frequency synthesizer. The CPPLL is used frequently for an analog front end, a VCO, phase detector, FD, and low pass filter with CP comprises a PLL, that is phase locked loop. VCO, which produces the frequency, consumes the most power in PLL. This oscillation frequency can be charged by modifying the control voltage. The design of the ring VCO is selected based on the oscillation frequency, phase noise, power, and tuning range. Initially, a suitable delay stage for the ring oscillator design is selected to meet the specifications. Furthermore, the aspect ratio, which is W by L ratio of the transistor in each delay stage is optimized to improve the required specifications. In these designs, the avoidance or minimum uses of passive components such as resistors and capacitors is emphasized to maintain the small and compact size of the circuit die area. The selection of an optimum number of stages for the construction of a high-frequency oscillator is an important part of the ring oscillator design. In a three-stage RO, frequent latch-up occurs to complete the appropriate start of conditions that should be achieved compared with even-numbered ROs. Therefore, a three-stage RO is selected to increase oscillation and concurrently reduce power consumption. The design consideration for the RO ILFD include division ratio, operating frequency, power consumption, and locking range. Therefore, free running frequency, power consumption, and locking range are selected to design the divide by 2 RO ILFD. The operating frequency of the RO ILFD is set according to the speed of the injector and the frequency of the selective block, which is constructed by the RO. Thus, the RO is defined as one of the focal points of RO ILFD design. The proposed RO-based ILFD consists of 3 differential delay stages. In the proposed RO ILFD, each delay cell adopts a fully differential topology with cross-coupled symmetric loads. The layouts of the ring VCO and RO ILFD are created using the 0.18 micrometer CMOS technology from Mentor Graphics. The VCO and FD of the IC layout area cover 1000 micrometer into 1000 micrometer to avoid wafer damage during cutting. The ground signal ground configuration is adopted for padding, in which the pitch between the pads is 150 micrometer. The VCO core occupies an area of 145 into 64 micrometer square without IO pads. The active area of the RO ILFD is 387 micrometer square without IO pads. The occupied area of the proposed RO ILFD is relatively small because the inductor and the capacitor are not used. The post-layout simulated output frequency of the ring VCO is 2.42 GHz, whereas the control voltage is set as 0.1 volt. A supply voltage of 1.5 volt is selected in the circuit to obtain this result. Simulation is conducted at different control voltages to validate the proposed circuit under a wide frequency range. A frequency tuning range of 80% is attained from 0.5 GHz to 2.54 GHz by applying 0.8 volt to 0 volt, which shows that a linear relationship is established between the control voltage and the oscillation frequency in the proposed architecture. IEEE 802.11b protocol is required to generate frequency ranging from 2.412 GHz to 2.484 GHz, and thus, the proposed delay circuit enables the ring VCO to work within this frequency range. The PN of IEEE 802.11b protocol must be set to minus 126 decibel per hertz at 25 megahertz offset to maintain a BER that is better than 10 to the power minus 5. In our design, a single sideband PN of minus 126.62 decibel per hertz at 25 megahertz offset from the carrier 2.42 gigahertz is achieved. Compared with the circuit of Turker et al., this ring VCO has better phase noise and high value of figure of merit at the expense of modest power. Its power consumption is significantly lower than other research works, which is only 2.47 milliwatt. Its wide tuning range, 0.5 to 2.54 gigahertz, is notable than other reported works. Compared with an LC oscillator, which heavily relies on inductor and varactor modes, the proposed RO ILFD circuit is designed and simulated using standard MOSFET models with reasonable accuracy. A free running frequency of 1.239 gigahertz is achieved when the control and supply voltages are set to 0.74 volt and 1.35 volt. The divide by 2 RO ILFD is simulated while the source voltage of the NMOS tail transistor for the first and second delay cells are biased at 0 voltage. The post-layout simulation of the ILFD confirmed that the circuit and corner variation work properly throughout the process when the supply voltage is within the range of 1.35 to 1.8 volt. The post-layout simulation is performed at different control voltages to validate the RO circuit under a wide tuning range. The RO has a moderate tuning range with extremely good linearity from 0.2 GHz to 1.2 GHz. The locking ranges of the divided by 2 RO ILFD at 1.35 volt and 1.8 volt, in which differential injection frequencies are injected at different voltages. At a supply voltage of 1.35 volt, the proposed ILFD with bias voltages ranging from 0.74 volt to 1.05 volt provides the locking range of 0.75 to 4.75 GHz, which is 145.45%. The locking range can be further enhanced up to 7.5 GHz, whereas the supply and control voltages are increased to 1.8 volt. Hence, the achieved maximum locking range is 163.64%. The present work achieves the widest locking range, that is 145.45%, compared with that of other research. The RO ILFD exhibits a wide tuning range with inferior PN because of the low Q factor of the RO. A novel tier switch is designed in the CMOS process to obtain better performance than that in other studies. The proposed tier switch includes 1 voltage source, 6 transistors, and 8 resistors. The proposed orientation of the transistor helps the tier switch obtain improved isolation between the transmitter and the receiver port, which eventually increases insertion loss. Transistor on-state resistance is a dominant factor that is responsible for insertion loss. Thus, only NMOS is utilized in the design because its conductivity is higher than that of PMOS. Gate resistance helps improve isolation by decreasing the effect of the capacitive coupling of the off transistors, whereas body floating resistors help perfect power handling capacity by retaining the high input impedance of the transistor and providing high source drain resistance to the body diode. The proposed tier switch provides a constant value of 31.5 decibel and 1 decibel insertion and isolation losses. Signals are shown to increase exponentially with input power. Moreover, a steady decrement is demonstrated with regard to the isolation of the tier mode. The large signal linearity of the proposed switch suggests that a high amount of power can be handled without any nonlinearity. From the results of the comparison, it is being seen that the overall performance of the proposed switch is evidently better and more suitable for RFID tag applications than that of the switches proposed in other studies. A wireless sensor network system consists mainly of 2 fundamental elements, the wireless sensor node and the data gateway. Essential elements of a wireless sensor node include a sensor, a memory, an RF analog front end, and a baseband processor. However, the overall performance of a sensor node depends mostly on its BBP because the BBP is the most computational and hardware extensive circuitry among all the units. A baseband processor is a device in a network interface that manages all the radio functions, or a chip that implements all the physical layer requirements for one or more communication protocols. Basic functions of a BBP include modulation, demodulation, encoding, decoding, and command execution. IEEE 802.11 protocol is widely used in WSN BBPs because of its popularity and power efficiency, which enables easy and accurate integration of wireless sensor into many different applications. Baseband processor must exhibit highly accurate channel estimation and bit error correction capabilities. 2 of the most important units of IEEE 802.11 based BBP, namely the forward error correction and channel estimator units. The channel decoder or FEC unit is responsible for correcting erroneous digital bit streams at the receiver side. In ultra-high-speed wireless communication systems, such as IEEE 802.11, the Viterbi decoder should work at a high speed with low hardware complexity. The overall performance of the baseband processor is stringent upon power efficiency and hardware complexity and accuracy of the Viterbi decoder and C units. The EEPROM architecture works in a bit-by-bit basis of data that needs to enter the memory cell array. Our aim is to decrease power consumption, and the deployment of the different components of EEPROM should be maintained as low as possible. A memory array with a memory cell is used to store data located at the intersection between word line and bit line. The The 2 kilobyte EEPROM array is arranged with 16 rows and 8 columns. The periphery circuits consist of a row decoder, which is used to select the active row, a column decoder, which is used to select the active column, data and address latches, a high voltage generator, a BL controller for the wire operation, and SA for the read operation. The EEPROM control logic manages the interface of the RFID tag digital controller for read and write operations. Among all the memory blocks of an RFID transponder, the most significant components are the sense amplifier and the charge pump circuit on the edge of CMOS EEPROM. The performance of the SA and the CP circuit significantly influence memory access time, that is read-write erase time, power dissipation, and the reliability of EEPROM. The SA consists of 3 inverters that use 3 PMOS and 3 NMOS. 6 IO pads are used in the SA design and are connected with the external sources and components. The proposed SA circuit detects 0 datum at 0 microsecond and 0.4 microsecond to detect 1, with the supply voltage and load capacitor set to 1 volt and 0.1 picofarad. The average current consumption during the read period at a maximum clock speed of 20 MHz is only 43 microampere. Moreover, the equivalent BL voltage of VDD is reduced to less than 1 volt, which proves that the SA can operate at a voltage as low as 1 volt. If the VDD becomes less than 1 volt, then the circuit will produce considerable noises. In addition, the proposed design SA consumes low power. An improved CP circuit is designed using a dynamic charge transfer switch. Diode-connected CP circuits suffer from threshold voltage loss, and a CP circuit with parasitic capacitors dissipate a large amount of power due to parasitic capacitance. To minimize power dissipation and minimize voltage gain or pumping efficiency, the CTS CP circuit method, which is suitable for the readerless RFID transponder EEPROM, is designed in this research. The CP circuit has no parasitic capacitor. The proposed CP circuit has 4 stages with pass transistor, which make the input for CTS control dynamic. The proposed CTS control scheme is developed to eliminate the body effect of the transistors, and the parasitic capacitors are eliminated from the proposed design to eradicate parasitic capacitance. The core layout of the proposed design is only 79.5 micrometer into 65.8 micrometer. 5 IO pads that are connected with the external sources and components are used in the CP circuit design. Defined supply voltage conditions such as 1.8 volt and 3.3 volt are set to test the CP circuit output. Temperature ranging from -25 degrees centigrade to 85 degrees centigrade is used to test the functionality of the CP circuit. After passing all the 4 stages, the enhanced CP circuit generates a higher output voltage with 5.62 volt because the modified circuit has no parasitic capacitor. The proposed circuit takes only 1 microsecond to obtain an output voltage of 5.62 volt. The pumping efficiency of the proposed CP circuit is compared with a higher VDD of 3.3 volt. In this stage, output voltage is 10.29 volt is achieved for the proposed CP circuit. The performance of the proposed CP circuit achieves the highest output voltage. Moreover, the designed CP circuit can perform faster, that is up to 50 MHz, which makes the proposed design superior to other design. The proposed design has the lowest power dissipation with 8 stages of pumping capacitors, which is better than that of others as well. Furthermore, the pumping efficiency of the proposed design is also better. So a novel readerless RFID transponder system that uses IPv6 and IEEE 802.11 protocol is presented. The proposed RFID tag can communicate with WNIC in IEEE 802.11 standard network without using an expensive RFID reader. In addition, the EPC provides all types of information regarding the objects by mapping with the extended address bit of IPv6, which also provides the physical location of the product or object. This work deals with the major modules of an RFID transponder, such as VCO, ILFD, TR switch, baseband processor, SA, and CP circuits, to introduce the readerless feature in the transponder that is compliant to the most established communication network, that is Wi-Fi. The wide tuning range, better pumping efficiency, readability, insertion loss, and PN performance of the aforementioned components are evaluated through post-layout simulation using mentor graphics tools. In the future, a readerless RFID transponder with a mapped TPC IPv6 address scheme will be a vital component of long-range communication networks. Finally, mobility, security, and scalability with the least implementation cost driven by the readerless RFID transponder system will be provided. Honorable Prof, this is a part of my academic journey for 10 years in UKM. I hope that Honorable Prof will accept my speech on behalf of the university. Thank you very much.